Well, hello, ladies and gentlemen. So today we're going to go over an application, an example involving the entropy balance. We already did the plane wall last time, but we're going to do a piston cylinder device containing H2O. So we're going to apply an entropy balance to a simple system, a simple process involving expansion of a container filled with H2O, piston cylinder device. And then we're going to move on to the property relationships. They're called the TDS, temperature DS property relationships that allow you to calculate the change in entropy of a system. These property relationships, the TDS equations, are similar. They're the same idea as the du-dh property relationship. Remember, du is equal to cv dt. And dH is equal to Cp dt, provided you're not within the dome. So we have similar relationships between temperature, pressure, and entropy given by the TDS property relationships. Now, these equations or relationships reduce to special forms when you're dealing with an incompressible substance, water, a solid, as well as forms, specific forms when you're dealing with ideal gas, both variable and constant specific heat. So we're going to go over an example involving an entropy balance today on a simple system, and then we'll go over, derive the TDS property relationships, and see what the TDS equations reduce to when you're dealing with incompressible or ideal gas behavior for variable and constant specific heat. That's the plan for today. All right, so let's get started here. We have a simple example. We have a piston cylinder device containing H2O. The H2O at state 1 originally is a saturated liquid. It's got a pressure P1 and a volume V1. What are these pressures and volumes? Well, initially the pressure of the saturated liquid H2O is 1.5 bar. And there is 2 liters of the stuff. So 0.002 cubic meters of saturated H2O inside of a piston cylinder device. Now, this piston cylinder device is insulated. So that's going to mean it's an adiabatic process. So if it's insulated, what are we doing with this H2O? Well, we have a little wire in here. So we're going to be doing electric work. How much electric work? 2,200 kilojoules of electric work from state 1 to state 2. So we're going to be heating up or boiling away some of the H2O saturated liquid. We're going to be boiling some of it away by heating it with a heating element. Also, the process is going to be an isobaric one. We're going to keep the pressure constant as we boil away the saturated liquid to presumably produce a saturated vapor. Okay, so what are we supposed to calculate here? We're supposed to calculate the change in entropy, delta S from 1 to 2 for my H2O system. So my H2O is a system in the piston cylinder device, so I want to find delta S. I also want to calculate the entropy generation, S gen from 1 to 2. Is the process electric heating of H2O in this piston cylinder device? Is this process reversible or irreversible? In other words, is S gen positive or 0? Remember from last time when we talked about S gen. If this heating process with the electric heating element is reversible, S generated better be 0. If S gen is positive, that means that the heating process is an irreversible one. So we're going to see here in a moment whether electric heating of H2O in a piston cylinder device is reversible or irreversible. Okay, that's the plan. So let's calculate delta S. Let's calculate delta S for the H2O. Let's do that first. Okay, delta S for the H2O. Delta S for the H2O system from 1 to 2. Well, that's going to equal the entropy at state 2 minus the entropy at state 1. Now, entropy is a property like enthalpy, like internal energy. So I can write this as the mass of the H2O times the specific entropy at state 2 minus the specific entropy at state 1. I don't know any of these things, so of course I need to use tables or some other means to get them so I can calculate delta S from 1 to 2. Let's look up entropy, specific entropy for the H2O at the initial state. I know the temperature and I know the quality. It's a saturated liquid, the quality is 0. So I can go to a saturation table and pull out the specific entropy at state 1. So S1 is S of a saturated liquid evaluated at a pressure of 1.5 bar. That's the pressure at state 1, okay? So let's go to our notes here, and let's look up the pressure saturation tables. So here's the temperature table here, B2. Here's the pressure table. Here's 1 bar, here's 2 bar. I don't have 1.5 bar, so I'm going to linearly interpolate between the two. Remember, specific volume, specific internal energy, and specific entropy. So specific entropy for a saturated liquid, so that's the second to last column, go down to 1 bar and 2 bar. I get 1.03, 1.3026 and 1.5301 kilojoule per kilogram degree Kelvin. So I'm going to interpolate that to 1.5 bar. So let's see here. That's going to be 1.5301 plus 1.3026 divided by 2. And I get 1.42 kilojoules per kilogram degree Kelvin. And that's from saturation table B3, saturation table B3, all right? Okay, so I have S1. There we go. That's a help. Now what about S2? Well, that one might be a little bit harder to find. I need to know something about state 2. I need to know several things. I need 2 properties. I need a pressure, a temperature, or a pressure and a quality, something. So state 2, S at state 2. So S at state 2 is S evaluated at a pressure 2, which is equal to a pressure 1. It's an isobaric process, and that's 1.5 bar. So I got the pressure at state 2. But I need one more property. I either need a quality or I need something. If it's a saturated mixture, I need a quality. If it's a superheated vapor at state 2, maybe I boil away all the liquid. I need a temperature or something. I need something. I don't have a temperature or a quality, but I might be able to get an internal energy. If I get an internal energy at state 2, I can get a quality at state 2. All right, so that's kind of where we're going with this. Let's see if I can get a quality and internal energy at state 2 and then maybe a quality. So let's apply the energy balance. Let's apply the energy balance and see if I can get U at state 2. Specific internal energy at state 2. So the E balance is Q 1 to 2 minus W 1 to 2 is equal to delta E 1 to 2. And if I neglect changes in kinetic and potential energy, then I have delta U from 1 to 2. All right? Now the work going on here is electric, and because it's an isobaric process and the piston is moving up and down, I have boundary work as well. So I have W electric plus W bound. Now the boundary work from 1 to 2, the boundary work, because it's an isobaric process, is equal to pressure times the change in volume. Okay? Now what that means is I can take the pressure times the change in volume and I can put it over on the right-hand side of the equation. And the delta U becomes a delta H. So I get a Q1 to 2. Oh, what's the heat transfer? It's adiabatic process. It's insulated. So 0 adiabatic. Okay, so the heat transfer is gone. So I get minus, and by the way, this electric work, this is done on the system, not by the system. So I'm going to get plus W electric from 1 to 2 is equal to delta H from 1 to 2. The boundary work term went over on the other side of the equation. And the delta U plus the P delta V became delta H because it's a constant pressure process, okay? Now, of course, this is equal to a mass times H2 minus H1. So actually, we're not going to get an internal energy to get state 2. We're going to get a specific enthalpy, H2. That's fine. If I have H2, I can get a quality. If it's a saturated mix, it doesn't matter. But I'm running into similar problems here. I don't have the mass. I don't have the mass of the H2O. I still don't have the mass of the H2O. I need that to get delta S2. Maybe I should calculate the mass of the H2O. Well, where am I going to put that? Let's do it right here. Let me get this first. I'm going to move this. The mass of the H2O. So mass of the H2O is equal to the volume of the H2O divided by the specific volume. Volume divided by specific volume gives you mass in the numerator. Let's evaluate this at state 1 because I know volume in state 1. Oops, I forgot to turn off the share here. Forgot to turn off the share. So energy balance applied to the H2O. Adiabatic process, no heat transfer. The work is electric and boundary. No change in kinetic and potential energy, so delta E became delta U. And I get the electric work is equal to M times H2 minus H1. Specific enthalpy. So I still need to get the mass of the H2O. Volume divided by specific volume will give me mass. Let's see here. At state 1, I know the volume. It's 2 liters or 0.002 cubic meters. So I'm going to evaluate this at state 1. Okay? That will give me my mass for the H2O. So I have B1. Specific volume at state 1 is equal to specific volume of the saturated liquid evaluated at a pressure P1 1.5 bar. And I can look that up. Let's see here. Let's go to the tables here. And I got 1.5 bar. It's going to be halfway in between. Specific volume is about 1.05. 1.05 times 10 to the minus 3 cubic meters per kilogram. 1.05. 1.05 10 to the minus 3 cubic meters per kilogram. Okay, so now I have V1. Let's see here. So 2 liters is what? There are, for 1 cubic meter, there's 1,000 liters. And then the specific volume is 1.05 10 to the minus 3 cubic meters per kilogram. Liters cancel out, cubic meters cancel out, and the kilogram goes upstairs. This 10 to the 3 and this 10 to the minus 3 cancel out. And it looks to me like I get just about 2 kilograms. I guess we'll be a bit more specific here. 2 divided by 1.05. So 1.9 kilograms. 1.9 kilograms. Tell you what, I'm going to write this down somewhere. I'm going to start running out of space. So oh gosh. So right down over here. It's a problem with only having two small boards. Right over here, I'm going to write right over here. MH2O 1.9 kilograms, okay? And also I'm going to write S1 as well. S1 is 1.42 kilojoule per kilogram degree Kelvin. Okay, we'll write stuff up as we come along, okay? All right, so to get S2, I need either an internal energy or an enthalpy, specific internal energy or enthalpy, to get a quality at state 2, so I can calculate the specific entropy, okay? All right, to do that, I need to solve for H2. I have M of the H2, so let's solve for H2. H2, divide both sides by MH2O, and I get W electric divided by MH2O plus H1. I don't know what H1 is. Let's see here. H1, I'll look it up in a table. H1 is H of the saturated liquid evaluated at a pressure of 1.5 bar. So I'll look that up in a table. Let's look that up in a table. Let's see here, 1.5 bar H. Going to interpolate between these two. Let's see here, 504.7 plus 417.46 divide by 2. So 461 is my H. 461 kilojoule per kilogram. That is H1. So I got that now. Okay, so H2 then. So you plug this all in and you get an H2. Oops, let me make sure I got this specific entropy right. 461. Let's make sure this is right. Is this internal energy? Whoops. I think I might have done that. Let's see here. Hold on a second. 417.46 plus 504.7 divided by 2. Yeah, 461. That looks all right. Okay, so H2 is equal to 461 plus W electric divided by the mass, which is 1.9 kilograms. Let's see here. W electric is 2,200 kilojoules. 2,200 kilojoules. So 2200 divided by 1.9 kilograms plus 461. And I get 16.189 kilojoules per kilogram. So that's H2. So H2, I'm going to write that over here. Instead. So 1618.9, I'm going to write that over here. 1618.9. H2, 1618.9 kilojoule per kilogram, okay? All right, so let's get equality at state 2. Let's get equality at state 2. So quality at state 2, done with the energy balance. So quality at state 2 is equal to H2 minus H of the saturated liquid at a pressure of 1.5 bar over HFG at 1.5 bar. And I get a quality of about 50%, 0.520, 0.520. Okay, so I go and crank through, won't go through the details here. So quality at state 2, I guess I'll put that up, 0.x2, 0.52, 52%. Okay, that's quality at state 2. By the way, let's put up a TV diagram here so we can see what's going on. TV, here's the saturation dome. Here's my 1.5 bar isobar. So we start off at a saturated liquid and we move to somewhere inside the dome. So there's state 2 right there, okay? There's the dome right there. Okay, so that's the process going on, isobaric expansion. Okay, so I got the quality at state 2. Let's calculate the specific entropy at state 2. We're getting there. Let's calculate the specific entropy at state 2. I got the mass. I got specific entropy at state 1. Let's calculate specific entropy at state 2. So S2 is S evaluated at a pressure P2 of 1.5 bar and quality X2 0.52. So this is going to work just like internal energy and enthalpy and specific volume. The same equation that applies for calculating properties inside the dome applies for entropy that applied for specific internal energy, enthalpy, and specific volume. So I'm going to write S saturated liquid plus the quality at state 2 times S of the saturated vapor minus S of the saturated liquid. Okay, let's look up some of these things. S of the saturated liquid at 1.5 bar. Let's have a look at that. I might have to do a little bit of interpolation here. Oops, let's do my screen share. There we go. Okay, so again, S of the saturated liquid at 1.5 bar. So that's going to be halfway between these two guys. So 1.53 plus 1.3026 divide by 2, and I get 1.41 kilojoule per kilogram degree in Kelvin, plus the quality at state 2, 0.52 times H sat vapor. That is going to be 7.3 594, oops, 7.3594 plus 7.1271 divide by 2, and I get 7.24. That looks pretty good. 7.24 minus S sat liquid, 1.41. And I get the specific entropy at state 2, so minus 1.41. And that's going to have units of kilojoules per kilogram, degree in Kelvin. So 0.52 plus 1.41, and I get 4.44 kilojoule per kilogram, degree in Kelvin. Okay, so that's S2. That is S2. .44 kilojoule per kilogram, degree in Kelvin. That's S2. Okay, now I have the specific entropy at state 2. So I can plug in. Let's see here, the mass again. The mass, let's go back. What was my mass? 1.9? A lot of stuff to keep track of here. 1.9 kilograms. 1.9 kilograms. 1.9 kilograms. And then S2 was 4.4 kilojoule per kilogram, degree in Kelvin. Minus specific entropy at state 1, which is 1.42 kilojoule per kilogram, degree in Kelvin. Kilograms cancel out, and I get kilojoule per degree Kelvin. Let's see here, minus 1.42 times 1.9. 5.75 kilojoules per degree Kelvin. Okay, so let's write that down here. The change in entropy of my H2O as it is heated isobarically and adiabatically with that heater is 5.75 kilojoule per degree Kelvin. Okay, entropy went up because we heated it up. Well, we boiled some of it away. Specific entropy of a superheated vapor, of a saturated vapor, is greater than that of a liquid. So our entropy went up as we boiled it away. Okay? All right, so let's calculate S-gen. Entropy generated from state 1 to state 2. What's S-gen? What's S-gen? Let's apply the entropy balance to our closed system H2O. Why? Because S-gen appears in the entropy balance. Maybe we can solve for the entropy, S-gen by the entropy balance. So S balance. Of course, the H2O is a closed system. H2O is a closed system, so we're going to write the entropy balance. What kind of version of the closed system entropy balance should we use for this problem? Do we want the differential? Do we want the overall process? Do we want the specific? Do we want the rate base? We had all those listed before. This is clearly an overall process problem. So I'm going to write the overall process entropy balance. Overall process entropy balance. So what we have is the sum of the heat transfer divided by the interaction temperature is equal to the change in entropy from 1 to 2 plus S generated from 1 to 2. So that's the entropy balance. Entropy being brought in from a heat interaction changes the entropy of the system, and there may be additional entropy generation inside. Okay? So that's how that equation works. That's how that equation works, all right? Now, this is an adiabatic process. This is an adiabatic process, so there's no heat interaction going on. So this term is zero. Zero adiabatic. Zero adiabatic. So that's gone. So that means that delta S, 0 is equal to delta S plus S gen. I'm sorry here, hold on a second. That is not the version. Let's see here. What do we actually write down? Where's my S gen? Is it over on the right-hand side or the left-hand side? Let's make sure we have this correct. Let's see here. There we go. Yeah, I guess I didn't quite write it this way. This isn't quite right. So what we have is, excuse me, what we have, let's go back to the proper equation. Delta S, what I've written is very similar to the open system entry balance, so let's not get ahead of ourselves. Delta S from 1 to 2 is equal to the integral. Sorry, I'm thinking about the open system entry balance. We're going to write the closed system entry balance. So delta S, integral of del Q over T from 1 to 2, and this is the interaction temperature, plus S generated from 1 to 2. That is the proper closed system entropy balance from the table that we saw last time. Again, this is an adiabatic process, so there's no heat transfer going on, so this term is equal to 0. Adiabatic. And we simply get the equation delta S from 1 to 2 for the water is equal to S gen. Let me flip the equation here. So this implies S generated for the heating process is equal to the change in entropy of the system. We have the change in entropy of the system. It's 5.75 kilojoules per kilojoule per degree Kelvin, okay? So S gen from 1 to 2 is 5.75 kilojoule per degree Kelvin, okay? Question, S gen positive or 0? S gen can't ever be negative. Entropy can only be generated, not consumed. So S gen is positive. Is this heating process a reversible? Is this heating process a reversible process or an irreversible process? Well, clearly S gen is positive, so it is an irreversible process. Electric work in general is an irreversible process. So note that this is greater than 0. Irreversible process. Irreversible process. All right? That's good. That looks good. All right, let's take a break here for a second.